Okay, so in this example, what we're going to do is just talk about how to identify the domain of our radical expressions. And you can see here what I have is 4 different examples that we are going to find the domain of. And I did provide a link over to Desmos that you can go to just to kind of verify that you have the domain correctly. But I might go ahead and check it in through this video and so on and so forth. But that's what we're just going to focus on. Oops. Is just the finding the domain of radical expressions. And again, the main important thing to understand for when we're dealing with the radical expression, for values that are included in the domain, they have to make the radicand, which is the expression under the radical symbol, positive. So what we're going to do for each of these problems, the first thing we're going to want to do, and again, we can work on this in like simpler terms, but the main important thing is everything that is under my inequality, I know needs to be positive. So I can say x minus 5 has to be greater than or equal to 0, right? This is the radicand, has to be greater than or equal to 0. Every single one of these, that's going to be the first step, okay? Because it can be equal to 0. As we showed, you can take the square root of 0, and that's going to be a part of your domain. But anything that's negative is not going to be in the domain. So by setting this inequality, what we're doing is we are solving for the values of x that are going to be defined for the function, which is basically the domain. So in this case, all I simply need to do to solve for x is just add a 5 to both sides. And therefore, I get x is greater than or equal to 5. Now, to understand the writing the domain, we could use set notation, we could use interval notation. I'm going to prefer to use interval notation, but I think to also understand this, it's really nice to use a linear inequality. And if you remember in the warm-up for this course, I talked about graphing linear inequalities, and we also talked about this like in Algebra 1 as far as how to graph an inequality. So let's just say we have a number line, and this number line just represents all x values. So here's 5. And it says x is the solution for all numbers greater than or equal to 5. So, if you're going to say number line, numbers to the right are positive or larger, and numbers to the left are smaller. So if x is greater than or equal to 5, that means all values to the right, 6, 7, 8, 9, 10 are going to be true. And 5, since it's greater than or equal to, 5 is going to be true. So that's what we call a closed point. We fill that in, and then we can just do a little number line like this, going like that. Now, how can we represent that? Well, we could throw this inside of, set. Like we could just say, there's the domain is within the set, x is greater than or equal to 5. And as far as interval notation, what we could do is say, well, 5 is included. 5 is a part of the domain, so that's why we're going to use brackets. And that's going to go all the way to infinity. And since infinity is not a number, then we're just going to use the open bracket as there. And that is a way to represent the domain in terms of an interval notation. And that's what I'm going to do for the rest of these is use this interval notation. Again, it starts at 5 and then continues to the left. So when you're using interval notation, the first term is like the farthest left and the right term is like the farthest right. And so you kind of go from left to right and then use brackets for included values and parentheses for non-included values. All right, let's go to the next example. Again, first step, radical, whatever it is, has to be greater than or equal to 0. So now I go ahead and solve. Hopefully you understand how this one I'm going to subtract 1 on both sides. 2x greater than or equal to negative 1, divide by 2, divide by 2. Now x has to be greater than or equal to negative 1 half. Okay, that's got really bad. Now, how are we going to do 1 half like on a number line? Well, again, guys, it really doesn't matter. You don't even need to use a number line. You could follow the same thing and say, oh, this is like the exact same here. It's just I'm going to start at negative 1 half and then go to infinity, which is basically true. But if you kind of like look at it as a number line, just make negative 1 half, like right here. Obviously, points to the right are going to be more positive, like 0, and then this would be like negative 1. But my domain in interval notation is going to look just like this. Negative 1 is included, and it's going to go to infinity because those are all values that are greater than negative 1 half, right? 0 is greater than negative 1 half. Negative 1 is less than, so we're going to go all values to the right. All right, so now let's look at this next one. The next one, it kind of brings into a interesting kind of twist. We can do this the easy way, or we could do it the more stepped way. And I'm going to do it the more step way, and then later in my examples, I'll quickly out. But the quickest way to do this, if you set this greater than or equal to 0, is just to add an x to the other side. However, if you want to use your inverse operations, let's do that. Let's subtract a 3. So we have negative x is greater than or equal to negative 3. And the reason why I want to do this is I just want to remind students, when we're getting this x to be positive, we don't want to solve for negative x. You got to solve for an x. So when I'm solving for this x, I need to divide by negative 1. And just remember, when you divide or multiply by a negative number in an inequality, you have to make sure you flip the sign. So therefore, x is now going to be greater than or equal to positive 3. So this is... Oh, I forgot to flip the sign. I was like, that's the thing. I just said flip the sign, and then I didn't flip the sign. So no wonder my confusion here. X is going to be less than or equal to a positive 3. So if we look at this as far as like on the number line, we put a 3 here, and let's say less than numbers would be 2, and here's greater than 4. So it's included, so we're going to use that. And then values that are less than 3 is going to be all the numbers to the left. Okay, so now it's going to continue going on to the left, which is going to be all the way down to negative infinity, right? As I keep on going more and more negative numbers, you can say negative infinity. And then it's going to go all the way to 3, and 3 is a part of the solution, so therefore it is included. And then last but not least is our lovely square root. Now this one can... I think it's best to make sense also to use test points. Like we can also go back through, and I'll show you kind of use test points. You could use test points for all of these, but I think just since most of us already understand inequalities, it's all right. But this one, it's kind of important to use our test points to at least verify that we did our math correctly. Because if you remember from our warm-up, they sometimes can be tricky. But anyways, first step, set it greater than or equal to 0, right? Because the radicand has to be positive. Now I can add a 2 to both sides. So I have x squared is greater than or equal to 2. Now, if I want to solve, I got to undo squaring, which is going to introduce the square root. And it's really important when we introduce the square root. Actually, you know what? Let's use that in red. When I introduce the square root, okay, we got to remember we got to take into consideration the positive and the negative version. And what's interesting here, what happens is when we take the negative version, the sign flips, just like we were multiplying and dividing by a negative number. So I'll have x is greater than or equal to 2. And x is going to be less than or equal to negative 2. And you might say, but why? Like, how does that make true? Well, that's where kind of test points can help us verify that that is the correct value. That you can take the positive solution as it is, but then when you take into consideration the negative version, you have to flip the sign. So let's kind of look at this. So we have negative 2, and then we have positive 2. They're both greater than or less than or equal to, so those are going to be both closed points. And that line goes there, and that one goes there. Now, let's look at the value 0, because if you're thinking, oh, well, why couldn't it be x is greater than negative 2? Well, that means 0 would be true then, right? Well, look what happens when we plug in 0. 0 squared is 0. 0 minus 2 is negative 2. Square root of negative 2 is undefined. Let's look at, like negative 3. Let's see if that works, because we're kind of wondering why the sign flips. If you plug in a negative 3, which would be like right there, right? Negative 3 squared is 9. 9 minus 2 is 7. You can take the square root of 7. So that is a confirmation of why this works. Now, as far as writing the domain goes, kind of sometimes gets a little tricky. You can see here we have kind of like two versions of our graph, right? We have the version where x is less than or equal to negative 2 and x is greater than 2. So we're going to do them separately. So if I was just going to write the domain for this graph right here, I would say negative infinity to negative 2. And if I was just going to write the domain here, I would say from 2 to infinity. Then a lot of times what you will see, and that's perfectly fine where it is, that's just your domain connected. A lot of times what you'll also see is us use the union symbol to connect them, and that just means they are part of the same domain for the same function. You know, these are together, they want to be included together. But that's just kind of your basic. We'll get into some more examples of finding the domain for radical functions here in a little bit later on.